Today's topic is on Pokemon. Okay, so here I have 4 different Pokemon, quite powerful, and at the bottom is what I want you to focus on. These over here indicate the types of Pokemon they are. Okay, so all the Pokemon in the world, they have a particular type. Sometimes they are a combination of 2 types. And I've got this box at the bottom of the screen to represent all the different Pokemons in the world. So if I want to list them down, I'll have, for example, Pikachu, Rattata, don't know how to spell, but doesn't matter, and everything is found inside here. Sometimes when you want to battle other Pokemons, you need to select types, certain types that will give you an advantage. So it is also useful to classify your Pokemon into types. So for example, I can have maybe a set of Pokemon. Let's call this set A, where A refers to Pokemon of flying type. So found inside A over here, looking at the 4 examples we have at the top, we've got Zapdos. We've also got Dragonite. Okay, because they are both flying. Then let's say we have another category or another set of Pokemon B. We call them Pokemon of maybe Dragon type. So over here, set B, we've got Dratini and again Dragonite. So we see that Dragonite falls inside set A and falls inside set B at the same time. So instead of separating these 2 sets like this, what we do is to combine them. Like this. Okay, so let's just beautify it a bit. Set B, we've got Dragonite and Dratini. So you see over here, Dragonite falls inside set A, which is a flying type. It falls inside set B, which is a dragon type. Okay, dragon over here, dragon over here. And where does Snorlax fall under? It doesn't fall in A, it doesn't fall in B. It is a normal type. So it may fall into another set of its own, a normal type. We just put it outside here, we've got Snorlax. Okay, so this over here is a form of classification that allows us to, at a glance, know which categories the Pokemon fall under. And this is actually a Venn diagram. Okay, inside this rectangle with these circles and names representing them, and all these Pokemon that are found inside, let me highlight all of them yellow, they are known as elements. So we say that inside this universal set, okay, so we use this symbol to represent the universal set inside this rectangle. The universal set contains all the known Pokemon. And inside this universal set, we've got categories, such as flying type, dragon type, and inside this category, we will just put on all the different Pokemons and we sort them out. Okay, so this is the introduction to chapter 4.1, Set Language and Notation. Okay, so instead of using what the textbook has suggested, these examples, I introduced it to you using Pokemon. Okay, so how do we actually represent and write set? We don't do it this way. This one over here that I've just shown you is just a non-mathematical way of categorizing them. So in our syllabus, we are going to use capital letters for names of sets. For example, set A. Set A contains subjects taken by students at Sec 4. So you see that we've got these curly brackets, and inside these curly brackets will be the description of the set. Okay, so in set A, we've got examples such as English, mathematics, and so on. Then we've got another different set. The name of this set is B, and it has stations along the east-west MRT line, which will of course include Tampines, Simei, so on and so forth. Then the objects inside the sets, they are known as elements. So like in our Pokemon case, the elements are just the different Pokemons. We hardly use this word members to describe them. And this is one way we can represent sets. Okay, we describe in words what the set contains. Another way of describing sets is to list down all the elements. For example, in set D, we've got north, south, east, and west. This does not describe the set, but it shows everything that is found inside, nothing else. In set N, okay, so this is the name of the set N. Again, we've got the elements 1, 2, 3, 4, so and so on. You can, the dots over there implies that there are more to it, and you can just imagine what else is inside this set. We've got 5, 6, 7, so and so forth, 1 billion, and it goes on and on. So instead of writing everything down, we can also represent N as, if you want to describe it in words, all positive integers. So this should be equal. Now these two, they represent the same thing. It's just different way of writing it. Okay, so over here at the side of our textbook, we've got set A, teachers below 30 years of age in the school, and set B, young teachers in the same school. So the question is, which one is well defined? It's quite clear that set A is well defined, because given the teacher's age, we will be able to tell whether the teacher belongs in set A or it doesn't. Whereas in set B, this word young is subjective. What's young to one person may not be young to another person. Right, next page. A third way of representing sets is like this. Okay, so you see all the n's over here, they refer to the same set. But now we have a third way of writing it. We write that inside set n, we have the elements, which are known as x. These are the elements. And this is the description of the elements. So how we read this is that n is the set of x, such that x is a positive integer. So from here I know that the elements inside n will be 1, 2, 3, and so on. So this is the third way of writing it. Now in set notation, elements, if small a is an element of set A, we write it this way: A is an element of set A. So the phrase over here, is an element, is replaced by this symbol. It looks like an E with a horizontal line in the middle. So if B is not an element, then we'll use the same symbol, but we put the dash across, just like our not equal to. Okay, so here it says that B, the element B, is not an element of set A. Remember, capital letters, they are used to represent sets. Okay, so you can understand these by yourself. So now take the next 10 minutes to try question 1, 2, and 3, and you may discuss with your and 4. Discuss with your partners. So I'll just do a few of question 1 for you. List the elements in each of the following sets in set notation. So our answer will be prime numbers less than 20. We've got 2, 3, 5, 7, 11, 13, 17, 19. So now I have rewritten set A, which is the description given as prime numbers less than 20, in another manner, which lists down all the elements. Okay, so now for part B. Now let's do part C. Part B you can try yourself. For part C, listing down all the elements, x is a positive integer and x is less than 5. So we've got possibility of 1, 2, 3, and 4. That's it. Nothing else. Okay, so try the rest yourself. So now I'll move on to example 1. Here we are given a set. The name is S. So again, capital letter to represent the name of a set. And the description of this set is letters of the word book. So part A, we want to express the set by listing its elements. We've got B as an element, O as an element, then O again repeated, and K. So in part A, it is simply B, O, and K. These are the elements found inside the word book. And take note, the set only counts distinct elements. So each element is listed only once. Although we see that the letter O appeared twice, we do not write it as. We do not write it like this because we've got repetition. Okay, and the other thing is that the order which the elements appear is insignificant. Whether you write it as O, BK, BKO, BOK, it doesn't matter. So part B is be an element of S. All we need to do is to look inside the set S. Do we see B inside? Yes. So we say B is an element of S. If we want to indicate in set notation, this is what we will write. B is an element of S. So you can try it one yourself. Just take 1 minute for this. In example 2, express the set A by listing its elements. This is actually found in your class activity question 1 part B, days of the week. So we've got Monday, Tuesday, all the way until Sunday. And part B is midday an element. Do you see this word inside our set A? Nope. We've got these 7 elements only, and midday is not an element. So we say midday is not an element. So it looks like C, but we do a stroke across. We try it too. Again, 1 minute. Now for something slightly more complex, example 3. It says that P has elements x, where x is an integer and x is greater than or equal to 1, so we can include 1, but it is less than 50. So if I want to rewrite this, I will have 1, 2, 3, and so on and so forth until 48 and 49. I cannot include 50. Then we've got Q. It has 1, 2, 3, 4, 5, 6 elements inside. Notice that set Q's elements, they look familiar. 25 is 5 square, then followed by 6 square, 7 square, 8 square, 9 square, and 10 square. So to answer part A, what are the elements of P that are also factors of 50? So elements of P that are also factors of 50, we place them inside curly brackets over here. So now these are the elements. Elements of P which are factors of 50. Then in part B, 8 square. 8 square is actually the same as 64. So the question is 64 a common element of P and Q? We can see that it is part of Q, but it is not found inside P. So the answer is no. So it's not an element of P, but it's an element of Q. And this is how we represent it. 8 square is not an element of P, but 8 square is an element of Q. Then in part C, this is a common type of question, but they give you the elements and you are supposed to come up with a description for it. In particular, they want you to express it in this form, the third form that we have learnt. So we can tell that Q is going to be, okay, it's got elements x, which are square numbers. It is a square number. But it is insufficient to simply write this, because, for example, 4 is a square number, 9 is also a square number, but they are not found inside set Q. So we need to place some restrictions. And we can say that x is between 5 to 10, inclusive. 25 and 100. Okay, so you can try it 3 by yourself. Okay, next we've got equal sets. Two sets A and B are equal if they have exactly the same elements. It sounds very easy because it is. As long as they have the same elements, they are equal. Must be exactly the same. So for example, let A be the letters of the word parallel. Okay, if I want to write it, if I want to list down all the elements, I've got P, A, R, E, and L. The order doesn't matter. Then B are the letters of the word apparel. So B, inside set B we have A, P, R, E, and L. So notice that I did not double count the letters even they appeared more than once. Okay, so is set A equals to set B? Let's do a check. We've got P and P, A, R, E, and L. They have exactly the same elements. So we say that yes, they are equal. Okay, so try it 4. You can just take 30 seconds. Next part is on subsets. If every element of A is also an element of B, then we say that A is a subset of B. Okay, before we move on, let's take a look at this. using the definition of subsets. If every element of A is an element of B, then A is a subset. Okay. In example 4, we've got all these elements of A. Okay, we've got all these elements of A, and inside B we've got all these elements of B. We see that all the elements of A were found in elements of B already. So based on this definition, we say that A is a subset of B. Then we can go the other way, and we also can say that in this particular example, B is also a subset of A, because every element found in B is found inside A, and they happen to be equal. However, if A is a subset of B, but A is not equal to B, subset but not equal to, then we say that A is a proper subset of B. And this is the symbol we use for proper subset. This one refers to proper subset. Okay, so we'll use some examples to understand what the differences are. Here I've got two sets, A, which contains 3, 5, and 7, and B containing 3, 5, 7, and 9. So we ask ourselves, is A a subset of B? So going to the definition, if every element of A is an element of B, then A is a subset of B. Okay, let's see. 3 is found inside B, 5 is found inside B, 7 is found inside B. So every element of A is found inside set B. So A is a subset of B. Then we look at the second term over here, proper subset. If A is a subset of B, which we have already concluded that, and A is not equal to B, then it is a proper subset. Now is A equal to B? No, because the element 9 is not found inside A. So they are not equal, but A is a subset of B. So now we fulfill the conditions to call it in particular A is a proper subset of set B. Okay, so since this represents proper subset, then this here represents not a proper subset. Now there is another symbol that is used to represent subset. It is this one. So here it is like, you can think of it as a combination of proper subset and equal. Okay, so this over here is a proper subset. Here we've got equal. Combine them and we get subset. Okay, so consider these sets. We've got C, D, E, F, G, H. C contains red and green. D contains red, yellow, green, and blue. Since all the elements of C are found inside D, and yet they are not the same set, we say that C is a proper subset of D. In the next one, we've got integers and rational numbers. all integers are rational. So that's just some recap. Integers will be 0, 1, 2, so on and so forth. We've got negative numbers also. Then rational numbers are numbers that can be expressed in the form a over b, where a and b are integers. So we say that yes, E is a proper subset of F. And the last example, G contains two genders, male and female. H contains two genders as well, female and male. So we say that these two sets are equal. We can also say that G is a subset of H. We can also say that H is a subset of G, but they are not proper subsets because they are equal. Okay, so example 5. A is the set containing elements which are the roots of x squared minus 4 equals 0. Okay, so this word root refers to solutions. So what are the solutions of x squared minus 4 equals 0? This is an equation which you can solve easily, where x is negative 2 or x equals to 2. So if you want to list down the elements of A, we've only got these two elements, negative 2 and 2, and this is the answer. So part B, set B contains one element only, which is 2. This element is found inside set A. And yet set B is not equal to set A, so we say that B is a proper subset of A. And this is the symbol we use for proper subset. The last part is a proper subset of C. Okay, C we've got elements 1, 2, and 3 are all the elements of A found inside C. So 2 is found inside C, but negative 2 is not found inside here. So we say that A is not a proper subset of C with this symbol. Okay, so take 2 minutes to try it 5 yourself. Go through example 6 and try it 6. You can take about 10 minutes for this. And this is the last part of the lesson on universal set. Remember I mentioned about the universal set when I introduced the lesson with Pokemon. So the universal set in this case contains every single element, which is every single Pokemon. And we use this symbol to represent it. Now in example 7, you are told to suggest a universal set using this is the symbol. Okay, in A we've got elements carrot, cabbage, celery, and lettuce. A is a set found in a universal set. And probably we can call the universal set for A as vegetables. So in a Venn diagram, this is what it will look like. Universal set, this being A. Okay, and for B, we've got elements of 2, 4, 6, 8, 10. So the universal set could be even numbers. And we've got set B being 2, 4, 6, 8, 10. So a representation could look something like this: 2, 4, 6, 8, 10. Then we've got other even numbers which are not found in set B, for example 12, 14, 28, so on and so forth. Now it is also possible for a set to have no elements, and that will be known as an empty set. And we use the symbol phi, read as phi, or we can just use fi for phi, or use brackets with nothing inside. So this is an empty set. Basically, there are things that don't exist. So an example is a set of men who are taller than 5 meters. We don't have people that are taller than 5 meters. So this is how we can write it. The set of men taller than 5 meters equals to phi, which is nothing. Then in mathematics, if we have x, where x is an element, that satisfies this equation. If you try to solve this equation, we've got x squared equals to -1, and we know that it is impossible to get a real number because we're going to be square rooting a negative number, so there is no answer. Then we say that the elements inside this set is phi, it is empty, there is no answer. Then the final point is that the empty set phi is a proper subset of every non-empty set A. Okay, so what this means is that a non-empty set A, for example, if A is represented by 1, 2, 3, then the set phi is actually an empty set. It does not have any elements. This is also found inside my set A, because A will contain an element that has nothing inside. I'll explain this more to you in class when I see you. Now the summary is that for every non-empty set A, so A must have something, and another condition is that A is not equal to the universal set. We say that A is a proper subset of the universal set, and at the same time the empty set phi is a subset of A, is a proper subset of A. Okay, this is the just two more examples to go through. Let A, the set A, be containing 0 and 1. So to list down all the proper subsets of A, we've got, if we don't consider the empty set first, quite clearly we see that 0 is an element, so the set containing 0 is a proper subset of A. 1 is an element, but if I write it this way, I'm calling this a set containing the element 1. This is a proper subset of A. And lastly, we've got the empty set, which according to our definition is a proper subset of A. So there are 3 proper subsets inside set A. Okay, so you can try it yourself. The answer will be very similar to what is in example 8. Please read this remark by yourself. I'll come back and I'll explain it to you. Last example 9. So we've got the universal set. X is an integer. X is between -2 and 4. We've got a set A where it satisfies the inequality 3x plus 1 is greater than 6, and one more set B with the inequality 5 minus 2x equals less than -3. So listing down the elements in the universal set, Okay, the elements will be -2, -1, so on and so forth until 4. The elements inside A, you just need to solve the inequality and list down all the values. So x is greater than 5/3, meaning that we've got the elements 2, 3, and 4. Then you should be wondering, why can x be equals to, for example, 2.5, since 2.5 is greater than 5/3? Then the answer is no, because the universal set, inside this universe, it says that x is an integer, and these are the only possible values of x. You cannot have anything else. So since set A is found inside the universal set, then we cannot have 2.5. It does not exist. That's why we only have 2, 3, and 4. Then in part B, we've got another inequality to solve, and x is greater than 4. So the question is B a proper subset of A? X greater than 4 means that inside B, if I list down all the elements, I've got 5, 6. No, we can't even have 5 and 6, because in the universe, it stops at 4. We don't have 5 and 6. So B is actually a null set. It's an empty set. Okay, so we represent it this way, or we can call it B equals to 5. Now, since the empty set is a proper subset according to definition, then B is a proper subset of A. The remaining time, do try it 9. And bringing back to the example of the Pokemon, what is an example of an empty set? So an example will be C, the set C containing Pokemon of robot type. So there are no such Pokemon. So inside this set C, there is nothing. This is an empty set. I spelled robot wrongly. ROBOT. Okay, so these are your homework questions due 28th Feb.